any product, any product would be then an eigenfunction of the Hamiltonian, and the sum of the energies will become the eigenvalues. So this is very simple. In a very simple statement, we said that the wave function for such cases is multiplicably separable, energy is additively separable. And from there, we tried to look at I can use chi for all these phi's, it doesn't matter. So we tried to look at a case where I is equal to j. We found that it's a symmetric, so this is okay for bosons, it's possible, but it cannot be a fermion. And if I not equal to j, it is neither boson nor fermion, so you have to symmetrize with the plus sign for bosons, anti-symmetrize for fermions. And a very similar anti-symmetrization is just not possible for I equal to j, because if I want to make minus, then because I is equal to j, this will become 0. So basic idea is that for the electrons, it is not possible to construct an antisymmetric wave function where phi I is phi j or chi I is equal to chi j. So in principle, of course, this is a statement of the Pauli exclusion principle. Then we further simplified. We said that for all r omega, we are going to use x. So for example, this will now become x1, x2, etc. Remember again, these are the definitions that I will change. For the spin orbitals from now on, I'm going to use, instead of phi, I can use chi. But that's a very minor problem, that everywhere I did with phi, but you can replace it by chi. All right, I think with this we will start today's class. Yeah, so this is so one of the important things to realize that while we will handle the many particle problem or many electron problem in particular, so we are now specifically talking about many electron problems. So let me again repeat some of the points. And we will look at, whenever we look at molecules in particular, for molecules, we are going to use Born-Oppenheimer approximations. So I'm going to come to that a little bit later. But this essentially means that I have an electronic Hamiltonian in the field of the fixed nuclei. So the nuclei positions are fixed, and I only have an electronic Hamiltonian. So I will define what I've called H electronic, and the solution that we are really seeking at is H electronic psi I, which I call it electronic now, of the coordinates, whatever the coordinates x1, x2, etc. Okay, equal to E electronic energy psi I x1, x2, etc. So this is something that we are really looking at. This is the solution that we are looking at. So everything is electronic. So I will define these terms under the Born-Oppenheimer approximation. So the whole idea, and the x is of course the composite coordinates of position and spin as I have defined. So please remember the x is nothing but the composition of r and omega. So you can write these as a vector. Okay. So what now needs to define is the electronic Hamiltonian. So very physically, the Born-Oppenheimer approximation states that since the nuclei are much heavier, the electrons, essentially the electrons adjust much faster than the movements of the nuclei. So one can define the electronic density or electrons in the field of fixed nuclei. Of course, nuclei will change, but this is an approximation that the electronic density and the electronic energy can be defined in the field of the fixed nuclei approximation. So that essentially defines the electronic Hamiltonian as an Hamiltonian over with a fixed nuclear coordinates. If you look at the total Hamiltonian, of course you have a system where you have kinetic energy of the nuclei. So I'm going to write this as minus half by 2m alpha. So I'm going to just explain this. Laplacian alpha. So this is the nuclear kinetic energy. Again, under the approximation of atomic units. where I have put 4 pi epsilon 1, h cross 1, electronic charge 1. So that is something that I'm going to keep using. And this is, of course, the mass, the atomic number of the nuclei. So since the mass of the electron is also in atomic unit 1, we don't write it, so only this number will come, which is basically the how much heavier the nucleus is compared to the electron. So that becomes the kinetic energy. And then you have similarly the electronic energy, which is minus half, so plus, minus half, and then you don't write. Yeah. So we actually are not writing h cross as well. So in atomic unit, h cross is also 1. So anyway, minus half Laplacian. This is a very simplified way of writing. Then you have the electronic, so sum over all the electronic coordinates. Then you have the electron nuclei interaction. So sum over I, sum over alpha. Alpha is again the nuclei. So you have Z alpha divided by Ri minus R alpha. So that's the electron nuclear attraction. Again, rest of the quantities are all 1. So, and then you have finally, of course, the repulsion energies, repulsion operators, which is first for the electron, which is 1 by modulus R minus Rj. And then for the nucleus, the two nucleus, let's say alpha and beta, where the atomic numbers will only multiply, and you have the R alpha minus R beta. So if you look at the composite Hamiltonian in atomic units, so this is in atomic units, so several things are 1. So the h cross is also 1, okay, in atomic unit. And then mass of the electron is 1. So in particular, h cross is 1, me is 1, and so on. And of course, the 4 pi epsilon 0 is also 1. And with all these, if you write the Hamiltonian, you can see there is a 1, 2, 3, 4, 5 terms. Out of that, the first two are the kinetic energy terms, electron and nuclei. Second one, third one onwards, are the potential energy. This is an attractive potential energy between the electron and the nuclei. And this is the repulsive potential energy between the electrons, repulsive potential energy between the nuclei. What Born and Oppenheimer did was actually to look at the analysis of the entire solution, for the total solution, and then found that if I define an electronic Hamiltonian in the field of a fixed nuclei, the error that is done, the error that comes up can be neglected. So it said, of course, there's an error, and we will not go, one can actually define by perturbation theory how much is the error in orders of perturbation, but we will not worry about it. At this point, we are saying that from here we can now define, since the nuclei are fixed, I am not interested in the nuclei kinetic energy. I'm not interested in the nuclear potential energy because this is just a constant, for example. So what we can do is to define a electronic Hamiltonian, which you now have only the electronic kinetic energy, which is minus half Laplacian. So this term, and of course the attraction of the electron in the nuclei. So this is basically, as you can see, this is picking up the terms which contain the electronic coordinates. So this term, first and the fifth term, are the two terms where electron coordinates simply don't appear, only nuclear coordinates. So you avoid that. The rest of the three terms are what is written. Once again, let me write here also the charge of the electron is also 1. Okay. So this becomes electronic Hamiltonian in the field of the fixed nuclei. So I don't write the nuclear part and the kinetic energy of the nuclei because that's not really important. The part which actually couples the electron and the nuclei is this part. These two parts are again depending only on the electron. But there is a simplification that in this case, the coordinates of the nuclei are fixed. So this Hamiltonian only depends on the coordinates of the electrons. I hope that is clear, because this is a fixed approximation. So for a given value of R alpha, I define an electronic Hamiltonian, And then what Born and Oppenheimer did was to show that one can write only an electronic part of the Schrodinger equation in this manner. Sorry. So one can get the electronic part of the Schrodinger equation and solve the electronic Schrodinger equation in the presence of the fixed nuclei. Okay, so if you do not worry about nuclei, then of course you don't have to worry about the kinetic energy in nuclei. What Born and Oppenheimer further did was that if I separate in this manner, then I can actually separate the electronic and nuclear problem separately. So, although the nuclear problem is something that we will not deal with in this course, let me write down how the nuclei will now, if I have to solve the nuclear problem, then of course I have to define H nuclear, right? And the H nuclear will of course have the nuclear kinetic energy. So I can define this as sum over alpha minus 1 by 2 m alpha Laplacian alpha. So that's the, of course, the nuclear kinetic energy. Then, of course, the nuclear repulsion energy will come. That is for sure. So nuclear repulsion energy will also come with the repulsive force. So if I had to solve the nuclear Schrodinger equation, then these two terms are automatic. But then I have to now take how the nuclei, what are the attraction the nuclei have with, because of electrons. So basically a corresponding term here. Now this is what the Born and Oppenheimer said, that this term will not appear like this because there the electrons are much lighter, nuclei are heavier. Here the heavy mass is moving. Before any change in the nuclear positions, the electrons will completely adjust. So what will come here is actually a potential which will be due to the electrons, due to the electronic wave function of the entire electronic problem. So when the electrons are moving, it is of course not just it is not just this. So the entire problem will come. So this will actually be E electronic. The entire E electronic will appear here as a function of R alpha. And this is something that is important to understand. For the nuclear problem, remember the R alpha, R beta are the variables. So everything is changing with respect to this. This is actually gives you the average nuclear, average potential energy that the nuclei face due to electrons. In which case, electronic kinetic energy, everything will come. Electron repulsion, electron nuclear attraction, everything will come, which is bundled here, which is basically the average value of H electronic with respect to the psi electronic, right? That's the Schrodinger equation. So this is going to come here. And now we will realize that this quantity, when we calculated, was calculated for fixed value of R alpha, R beta, etc. So this quantity in terms of R alpha, R beta can be considered as a function of the nuclear coordinates. Obviously, when we solve this, we solve for a specific nuclear coordinates. But if I solve this for all nuclear coordinates, that means I solve the Schrodinger equation, this Schrodinger equation repeatedly, then I can get a function which is the electronic function as a function of R alpha. So this is very, very important. And this is also a potential to the nuclear problem. Clearly, I write the first term of T nuclear, which is kinetic energy. Kinetic energy is often represented by T. These two terms together, I can now write the potential energy. So, of course, each operator has a kinetic and potential energy. Each Hamiltonian, has the kinetic and the potential energy. So, this together becomes the potential energy which will depend on R alpha. So, it's very important to realize that the V of R alpha, which I now am defining a new term, is the potential energy operator for the nuclear problem. And there is a nice name that is used, that this quantity is called potential energy surface. So if I actually plot this, so if I plot V of R alpha, now this is a very schematic plot as a function of R alpha, all R alphas. It's of course very multidimensional plot, but I'm schematically saying this will actually become the potential energy surface. Now, it is very commonly known that you have done in spectroscopy as well as in previous quantum mechanics that for hydrogen molecule, for example, H2 molecule, if I plot a similar curve, then because of the fact that the H2 molecule has only 1 degree of freedom, that's the 3n minus 5, 1 degree of freedom, I can write the potential energy as a function of only distance between the hydrogen, and that's my R alpha. And this is a very famous curve that all of you know. It's a Morse curve, right? So this energy dips, and this is where the hydrogen is more stable, minimum energy, and then goes up. So this becomes my hydrogen plus hydrogen energy. So this actually dissociates two hydrogen atoms. So very often this is known as a Morse potential energy curve for the hydrogen molecule. Of course, for hydrogen molecule, it's very easy to draw. Okay. So these kind of curves are called potential energy surface. If you look at my electronic structure problem, and this is my electronic structure problem, I'm first solving this for a given R, given nuclear coordinates. So now think, how do I generate this curve? To generate this curve, I have to generate this solution for every value of the coordinates. So let's say hydrogen molecule. For every hydrogen distance, I will have to keep doing this. So it's not one calculation. I have to repeat this electronic part many times. Once I get the electronic energy for every R, then all I have to do is to add this Z alpha, Z beta by R alpha. That is very easy because this is just a constant. For a given value of R alpha, R beta, this is constant. I simply add this to this electronic part, and then I can get the potential energy surface. This is a very important quantity, although in our text we will not mention this. This is a very important quantity if you want to solve the nuclear problem, as you can see, because this becomes the potential energy for the nucleus. So this is very often required when you do dynamics. In fact, some of you have already done some course on dynamics. So dynamics essentially requires this, because dynamics looks at how the nuclei move. So very often, but to get this, I have to solve the structure problem. So this is called the electronic structure problem. If I solve the structure problem for all R alpha, add the nuclear potential energy, then I will get what I call the potential energy surface for dynamics. So you cannot do dynamics unless there is a structure. I hope you understand, because to do dynamics, I require the electronic energy as a function of R alpha. And I actually have to calculate this for all R alpha, which is a very, very time consuming part. And for hydrogen molecules, it may be easier, but for polyatomic molecules, it's very, very complicated stuff. So that's the problem of dynamics. So this is very often called the potential energy surface. So the structure, so the electronic structure can give you or gives you the potential energy surface, which I'm just calling PES, the potential energy surface, which is used in dynamics. Now, why is it potential? It is actually a potential not to the electronic problem. This is a potential to the nuclear problem. And that's the reason it is called the potential energy surface. Okay? So I have to do a complete structure calculation, then only I can do dynamics. So very often there is an adage where structure ends, dynamics begins. It is very important to realize that the dynamics people are actually dependent on the electronic structure, even to start their calculation, if they really want to do correctly. Obviously, it's not possible in many cases because the electronic structure requires a lots of calculations for a polyatomic molecule. So what most of the dynamicists do is to take some approximate potential energy surface. So you will see maybe from reasonable electronic structure problem, not with so many R alpha, with some coordinates, then extrapolate and so on. So there are lots of approximate surface, and then they can do dynamics. Then of course you solve the nuclear Schrodinger equation. Okay, so I'm not going to worry about the nuclear Schrodinger equation, but I would just write it down that eventually you have H nuclear, which is just exactly where it is written here. H nuclear, this is T nuclear plus V of alpha potential energy surface. So this H nuclear gives you the phi nuclear equal to E total phi nuclear. So you can actually calculate the total energy from the solution of this, because this now has everything. If you remember, this H nuclear contains the kinetic energy in the nuclei. It contains the electronic energy as a function of R alpha. So all the electronic kinetic energy, electron nuclear attraction, electron repulsion, everything is included here. And then of course nuclear repulsion. So that quantity actually consists of all the 5 terms. The first term is already there, fifth term is already there. The middle 3 terms appear in disguise as electronic energy. So electronic energy as a function of R actually has everything. And that is what is being added to the nuclear repulsion to give you the potential energy. So we can solve this. Of course, this is dynamics. We are not going to worry about it. But I just thought I will give you a passage connecting electronic structure to dynamics. As of now, our interest is in the electronic structure problem. So let me rewrite the electronic structure problem. So I have H electronic, psi electronic equal to E electronic, psi electronic, where H electronic is a function of the electronic coordinates in a field of fixed nuclei. So many times people write it in this manner, that it is H electronic as a function of R1, R2, etc. Then semicolon, capital R1, capital R2, etc. It means this is actually a function of electronic coordinates for a given value of nuclear coordinates. The reason it is often written is to remind you that if I change the nuclear positions, this Hamiltonian will change. And of course, the electronic energy will change. The wave function will change. Everything will change. Hence, it's to remind you, but note that when we go forward, we are never going to write it. So this will be actually underlined. You remember it, that everything that I'm writing is for a given value. So they become like parameters, you can say. And these are my variables. In a very strict mathematical term, the nuclear coordinates become parameters. So I change the nuclear coordinates. I have a new Hamiltonian. Everything is different. Okay? So this is exactly what we are going to solve. And then I'm going to bring to the earlier passage that I did yesterday how this problem is actually very complicated for atoms and molecules. Okay? I mean, of course, the Born-Oppenheimer approximation refers specifically to the molecules. So I can stick to the molecules in general. So this particular problem of electronic Schrodinger equation, giving you electronic structure, is a very, very important problem. And this is something that I discussed. It's a problem where the accurate calculation of the electronic energy is very important, because most of chemistry, I told you already, is associated with the differences of energies of two large numbers, two states, which are very large number. So in that sense, this is a very, very important to find out these quantities very accurately. Okay, so that is the reason we want to solve this very accurately. And as we will see, for cases that we are interested, the exact solution of this is not possible. That is something that we will see. I want to now mention that as we go forward, we will drop these unnecessary superscripts because they don't add any value as long as you remember that what we are doing is electronic structure problem. So we will simply write H psi I equal to EI psi I, and you should remember that this is completely electronic problem. So I'm not going to write the superscript because they become very cumbersome. So I go back to my earlier theme that I want to essentially solve this Schrodinger equation. So these are my stationary states, and this is connecting to the quantum mechanics, that these are my stationary states of energy, and I will get the energy as E of I. For any given psi I get E of I, and there is no uncertainty in measurement. So the average value is same as EI, but actually if you make a measurement in Copenhagen interpretation, all for an identical systems, or ensemble of identical systems, which is basically a thought experiment, all the robots which are observers will get the same value EI. So that's basically to say there is no uncertainty in the measurement. So that is what we are trying to find out. Okay, what we have learned is that if this Hamiltonian, let's say for two particle, 1, 2, would have been H1 plus H2, then this problem was completely solvable. That is what we have learned in the last class through the non-interacting theorem, because all I had to do was to solve the eigenvalue equation of small h, which is one particle, then construct the wave function as a product, and particularly for electrons in the antisymmetrized product, and then get the energy as a sum. I had already written down that the wave function is multiplicably separable, energy is additively separable, right? The problem is, if you look at the electronic Hamiltonian, the problem is that is not the case. So the problem is, this is the electronic Hamiltonian. If you look at these two terms and these two terms are separable. This second term, these two terms are separable as a function of I. So I can write this as minus I Laplacian, sum over alpha, Z alpha Ri minus R alpha, whole thing sum over I. So this can be completely separable. The problem comes because of this third term. This is the electron-electron repulsion, which cannot be separated. So let me write down this H, which is the electronic Hamiltonian now, in our actual electronic Hamiltonian, as a sum over I minus half Laplacian minus sum over alpha Z alpha divided by Ri minus R alpha, plus so this, the same electronic Hamiltonian I have rewritten. The sum over I have taken for the first two terms as common, and I have minus half Laplacian. This is, remember, this is fixed in Born-Oppenheimer approximation for a given value of R alpha. Then what I'm defining, I can define this term as some one particle Hamiltonian in terms of the electronic coordinates. It's a single particle I. So let me call this h of I, small h of I. So let me write this as sum over I, h of I, plus I less than j, 1 by modulus Ri minus Rj, where h of I is nothing but minus half Laplacian minus sum over alpha Z alpha Ri minus R alpha. I hope it's clear. The sum over I have taken out. So sum over I, h of I. So h of I is basically 1 in the bracket. And you can see it's a single particle Hamiltonian, just depending on the coordinate Ri. But then there is a second term. This term is not separable. So I cannot use the non-interacting theorem. So to say that this electronic Hamiltonian is now an interacting Hamiltonian. So I hope I'm able to explain to you that all that we learned in the non-interacting theorem cannot be applied here because of this term. However, that learning will be very useful as we'll go to the Hartree and Hartree-Fock theory. But in the case of an exact solution, one by modulus Ri minus Rj can be written as some f of I plus some f of j, let's say. Then the problem would have been completely solved, because these are again two one particle operator. I would have patched it up with this h of I, and the whole thing would have been sum of one particle operators. But unfortunately, this is not possible. There have been a lot of mathematics. So you can say, okay, this is a mathematical problem. Yes, indeed, this is a mathematical problem. And the problem point is that this is insolvable. So I cannot separate this operator as a sum of two one particle operators. And this is where the entire quantum chemistry is hinged. Since I can't use non-interacting theorem. I can't use the total wave function as a product or antisymmetric product. That's a mute point here. Or the energy being additive. I can't use any of those non-interacting theorem solution. So I have to look for a solution now in a different way. And this is where the quantum chemistry tends to get exciting. What is important also to realize that because of this, the exact solution is not possible. So, whole of the quantum chemistry, we will resort to approximate solution. It's important to realize that the whole of quantum chemistry would be actually to find out approximate solutions, since exact solution is not possible. How do I get approximate solutions will be the main text of this course. We also need to find solutions, and this is very important for the theory, need to find approximations which are, and this is something that I'm making a statement at this point, we will come back and explain, which are systematically improvable. Which essentially means I should know that there's a hierarchy of approximations, say A1, A2, A3, etc. I should know which is better than what. And how do I achieve from, let's say A1 is the worst, A2 is the next best, A3 is the next best. How do I go from here to here and then further? What is the system of improving? If I can never reach the exact solution is not possible. But if I know how to systematically improve, at least I have a handle on saying that this is as good as this. I don't want to go beyond because it is more complex, but at least I know I have reached A3, which is better than A2, better than A1. I think that is going to be one important goal of the quantum chemistry. Then I know that A3 should give a better result than A2, better result than A1. If it does not happen, one has to worry, because this is a better approximation, right? Many times it used to happen, and it still happens, that you use sometimes a set of bad approximations and you get a better result. Okay, I don't want to tell approximations which are probably not sound theoretically, and you still get better results. So standard approximations used to be semi-empirical approximations like CNDO, Huckel, and so on. They used to give very good result because they're tuned with experiment. So you cannot defend theoretically how they are good. Density functional theory has similar problems, very often DFT. But the solution that we will look for in the ab initio, or I will define ab initio just now, for this electronic part will be systematically improved. Systematically improvable. That is very important. You don't have to necessarily improve it, but you should know how to improve it. They're improvable. Okay? So very often in electronic structure theory, we paraphrase, it is not important to get just the right results, but you must get the right results for the right reasons. I think this is very important. You can get right results for wrong reasons. What does it mean? It means you make two errors, they may cancel each other, and you can get right results. But what is important here is to get right results for the right reasons. The approximations that we'll also develop will not be of the kind of semi-empirical. So no recourse to experiment. They will be completely theoretical. And this kind of approximations that we will discuss here are very often called the first principle approximation. It means we are developing approximation from the first principle, from the very first principle, without any help from the experiments. Of course, numbers, results that we get will be compared with the experiment. Results that we get will be used for prediction of experiment, new experiment. But the theory per se, to obtain the results, to obtain these results or obtain the solution of this electronic part of the Schrodinger equation, we will not use any experimental numbers. The semi-empirical theories actually used to use the experiment numbers, but we are not going to do this. So in that sense, this will be called the first principle approximation. There is another word for this, and I'm going to introduce this, and that is called the ab initio approximation or ab initio methods. The ab initio is actually a Latin word. It's a Latin word. It means from the beginning. I hope you can easily understand because this has English origin in some sense. Initio is initial. So it starts from the beginning and then you develop. That means I don't assume any experiment results. It's purely theoretical. Sometimes it is called first principle. Sometimes it is called ab initio. Before I move over, and that will be in the next class, I must mention that ab initio is not exact. I think that's now very clear. Because no exact solution is possible. We are only finding approximations which are systematically improvable, but without taking experiments. Since they're systematically improvable, whatever right results I can get, I can justify that you have got for the right reasons. Many people feel that ab initio means exact. So please understand, ab initio is not exact. Ab initio is also an approximation. In fact, there are several approximations which are all systematically improvable. So I have several ab initio approximations. All of them ab initio, but none exact. So the example that I gave, for example, A1, A2, A3, three approximations, none exact, each ab initio, which means none of these take recourse to the experiment. So that will be the emphasis of this course. So in that sense, we sometimes say it is a very purist course, pure quantum chemistry, that we are going to do Abhiniti approximations. So as we see, we will develop a series of approximations. And the leading first approximation will be the Hartree-Fock approximations. I think we will come to that much later, but I just thought each of them will be ab initio. So there is nothing called one method. So it's a plural is very important. There are ab initio methods, ab initio approximations, and all of them we have to understand which is better than what. That's the focus of this course. All that, I again repeat, because the Hamiltonian, the electronic Hamiltonian, is not separable. I just want to repeat it to start with. It is not separable into one electron Hamiltonians or in one electron Hamiltonians. So all that we are doing is because of this. Don't forget this. Is not separable because of the electron-electron repulsion operators. And because of that, we have to develop approximations. But we are saying that we will develop approximations which are ab initio in nature. I hope it's clear to all of you that I basically set the standard of this course now. So there are a few important things that we want to say, that our course is on the electronic Schrodinger equation. In Born-Oppenheimer approximation, that's something that we have discussed. And since the electronic Hamiltonian is non-separable, we will develop a series of ab initio approximations. So that would be our emphasis of this course. Okay? Of course, before we do that, we must understand that a separable Hamiltonian gives us a lot of nice picture. The chemistry becomes very simple. So while this is non-separable, our tendency will always be to go back to a separable Hamiltonian, see what it gives, and then go forward. So I think that is a very important part that you will see as you go forward. We should also remember that whatever wave function we'll build must be antisymmetric. We will discuss, however, in fact, that will start in the very next class in the evening. We will discuss separable Hamiltonians many times. Several times we will discuss in this course, simply because we learn from here. Because the fact that our H is non-separable is only because of one term. Don't forget. Without that term, H was separable. That's electron-electron repulsion. So we will try to understand that how close this Hamiltonian is to a non-separable Hamiltonian. So many times in the discussion, we will go back to a separable Hamiltonian to understand lots of things, lots of chemistry. In fact, you will see that the Hartree-Fock approximation, which is the first approximation, is one that is actually a separable solution. Because remember, all the separable Hamiltonians have much better connection with the chemistry, simply because they can be written in terms of orbitals. So I just want to end by telling you the non-interacting theorem of the separation. That if your Hamiltonian is H1 plus H2, and they have solutions, H of 1 is chi I1. I'm now writing chi I explicitly, not phi. EI chi I1. H of 1, H of 2 is chi j2, Ej chi j2. Of course, these 1 and 2 are dummy. Then the psi 1, 2 would have been an anti-symmetrized product of chi I1, chi j2. I think we discussed this already, that the wave function would be multiplicably separable, except that for the electronic problem, I have to introduce an anti-symmetrizer. And then I know that I equal to J, the anti-symmetrizer chi I1, chi J2 will become 0. And that's the statement of Pauli principle. However, this simple discussion that the electron 1 is in a spin orbital chi I, electron 2 is in a spin orbital chi J, was possible because of the separable Hamiltonian. In exact case. In the real Hamiltonian, where there is an additional term, this will become now an exact, this will now become an approximate description, not an exact description. However, this approximate description will be very useful to understand the chemistry. And all of chemistry that you do, where you say one electron is in orbital this, another electron is in orbital this, has a mapping with the separable Hamiltonian. For example, when I say helium atom is a 1s alpha, 1s beta, ground state, right? It means electron 1 here, electron 2 here, anti-symmetrizer, right? This very thinking is linked to a separable Hamiltonian, right? Because otherwise it cannot come. I showed you. However, although it is linked to a separable Hamiltonian, we know in real case our helium Hamiltonian is not separable. And this is where there is a difficulty in teaching a pure quantum chemistry, where you develop very good approximations to a very simple concept the way chemists understand. And this has been one of the bottlenecks of learning quantum chemistry, because we are already fed in chemistry with the concept of a separable Hamiltonian only. Because without that, I could never give such a picture that one electron here, one electron there. Anti-symmetrizer is not an important point, okay, which is where it doesn't matter. But I have two electrons, two spin orbitals. This concept is built in the idea of the separable Hamiltonian. But in actual case, it is not separable. So we will come back to the separable Hamiltonian many times for discussion's sake, for understanding, but we'll have to go forward. So I think we will start from here for a 2-electron problem, so at 6 o'clock. And I also want to tell you that the 4th class that has been given is also for discussion. And any class test, of course, I'm not going to take class test today, but later on class test, if there is an assignment to be discussed and so on. But I will spend some time on discussion in the beginning, before I actually introduce the new topics, okay? And a very good way to understand is always the 2-electron problem. Because that's the first problem beyond one particle problem, beyond one electron problem. And this is very simple. So most of our discussion will be hinged on a 2-electron problem. All right, if there are any more questions, otherwise I'll close now. It's 4 o'clock.
Hello, sir.
Yes.
A question about the potential surface, how it comes
Yes.
the function of the nuclear coordinates, that is
Yeah.
written Ri.
Yeah. Yes.
There is.
Right. How it becomes?
Because potential must be the electronic coordinates
No.
are.
This is called the potential to the nuclear problem. See, the nuclear Hamiltonian, when I write the nuclear Hamiltonian, this is the kinetic energy and this is potential for the nuclear problem. So that's a common mistake actually. Potential energy surface is called potential energy because it's a potential to the nuclear problem. And that is what I have shown. However, this comes from the electronic Schrodinger equation, because one part of this V of R alpha is the E electronic R alpha. But
So
then I
also,
add, yeah.
also the nuclear coordinate also included. So
Yes.
E nuclear also
Yes.
are alpha function. That matters.
Right. So this plus this is this. This is T nuclear, right?
Yes, sir.
Second and third term is the V.
Mhm.
So that is why it is called the potential energy to the nuclear problem. It is nuclear repulsion energy, but this is how the nuclei adjust with all the electrons. And there it is not electron nuclear attraction only. It is everything about the electron, which means kinetic energy, electron repulsion, everything is built in here. That is because nuclei move, as the nuclei move, electrons have already adjusted. They are much faster. So the electronic
Oh,
energy is important for the nuclear potential energy. So that is why you get confused,
oh,
because
yes,
you
and
actually, you actually solve this to get this.
oh, okay, okay, I understand
But
now.
yeah,
Yes.
but this is the potential to the nuclear problem.
Oh, okay, okay,
Yeah, so this is very confusing actually. In the dynamics, they have to explain this properly. I'm not going to do the dynamics, but it's important to understand this. And that is the reason I said where structure ends, dynamics begins. I hope you understand this meaning.
okay, sir.
Because you have to get the electronic as a function of R alpha, then only you can get V of R alpha, and then only you can do the nuclear Schrodinger equation. So I have to first complete the electronic structure problem, which is impossible to do. Well, how many times you are going to solve it? So of course you have to take approximate V of R alpha and then do it, the nuclear problem. Is it clear?
Okay, sir.
Okay. Any other question?
No.
Yeah, okay, otherwise I'll come out of this. So the next class is at 6 o'clock.
Yes, sir.
Yeah, so